last machine learning coffee seminar session for this spring term. We'll have a summer break now and thought to continue on 14th of September, but stay tuned in the mailing list and the website on more precise details on this. It would be very nice to have the sessions face to face at that time, but yeah, it remains to be seen. Anyway, today we have one more great speaker, Jussi Jokinen from Aalto University, talking about multitasking and rational hierarchical control. And just a reminder for all in the audience, we again have a nice crowd. The speaker welcomes questions midway. It would be actually nice to have a bit lively events in these talks. If you'd like to ask a question, please write it to the chat, or even preferably click the raise hand button and I will then give the floor to you. There will also be time in the end for discussion. Jussi, thanks for joining.
Thank you, Sami. And thank you, Kaola and others for organizing the details in here. So hi, yeah, I'm Jussi Jokinen. I'm a postdoc here or there at Aalto University, working in Antti Oulasvirta's user interfaces group. Now I'm a cognitive scientist, but I work a lot with machine learning topics. So let me first position myself and today's talk using this nice Venn diagram. So in the red here, we see cognitive science. And what I do is I create computational models of human cognition. Now, in order to do this, I need help from machine learning, which is the green circle here. Machine learning gives us algorithms and models that are able to perform complex cognitive tasks. So I use that to create computational models of human cognition. Now, I mainly work in the intersection of the red and the green, that is in the intersection of natural and artificial cognitive systems. I rarely do anything related to neuroscience itself. However, even if that's the case, I need to make sure that my models are biologically plausible. And that's also what I'm going to do today in my talk. So today's talk is about rational hierarchical control. And let's get into it by defining some of the basics here. Let's start with control. So what is control? A dictionary definition for control would be that to control something is to exert authority over it. So for example, I want to drink coffee, so I need to exert control over my hand so that I can get the coffee cup into my hand and bring it to my lips. Similarly, a robot needs to be able to control its hand so that it can do what it's programmed to do. A key concept here is a control policy that maps the states of the task into actions that need to be carried out in order to proceed in the task. Now, the problem of machine learning would be to come up with methods for discovering these control policies. And similarly, the problem of cognitive science in this context is to figure out how the human brain discovers these control policies. To help us in this question, I'm using a really popular and widely used method called reinforcement learning. And I'm sure that most of you are very familiar with this topic, so I'll just very briefly cover the basic concepts here. We are describing here an agent that works in a world and tries to solve a problem. And we specify this problem-solving sequence as a Markov decision process. So there is a world that is in some state S. The agent may take actions that transition the world according to some transition function T into another state. To reflect the fact that the agent has goals, there is a reward function that generates real valued rewards from taking actions in some states. Now, to solve the problem of control policy in these sorts of descriptions of problem-solving tasks. Reinforcement learning employs generally two classes of methods. There is the model-free reinforcement learning, where learning occurs by updating value of individual actions. And this happens by computing reward prediction errors. So while being in state S, the agent makes a prediction, what's the value of taking action A here. Then the agent observes the reward, computes how wrong it was in this prediction, and updates the value. Thus, it learns. There is another way of solving this problem that is based on models. So the agent, by exploring the world, learns the transition model T and the reward model R. And using internal simulations, using these learned models, it can plan ahead, try to predict what's the value of different actions in the situation it is in. Optionally, we can augment this Markov decision process by noting that the agent may not know the actual state of the world. It can only make observations, and then based on those observations, it has observation history, and it can summarize the observation history using a belief state. Now, in any case, whether it's model-free or model-based approach, the goal is to discover an optimal policy. So we define a pipe as a policy that maps action, states action into probabilities. So given a state, it gives probabilities of actions. And optimal policy is defined as something that maximizes the value function. And I won't go into the details of this equation. I'm sure that most of you are familiar with it, but the idea is that the agent following an optimal policy takes actions that not only result in the highest immediate reward, but also in the best long-term cumulative gain. Now, this is the machine learning side of this approach, but then a pertinent question for cognitive science is this sort of a set of computations feasible to represent how the human mind and the human brain learns and solves problems? And it turns out, yes, but obviously with a lot of caveats. Now here is a very, very simplified illustration of the human brain. And I have highlighted just some of the parts of the brain. First, I'd like to focus on the red circle there, midbrain. We know that the midbrain in the mammalian brain does something that is rather similar to computing these reward prediction errors. So the midbrain makes a prediction, and then it gets a feedback, and then based on the error, it produces or releases dopamine. And this dopamine is used to strengthen the connections in the striatum. And there is plenty of evidence that this sort of interaction between the midbrain and the striatum using dopamine does implement something very similar to model-free reinforcement learning. So the striatum represents states and actions, and there are connections between these states and actions, and the dopamine released in midbrain strengthens these connections when learning happens. Of course, we still don't know how the states are exactly represented in the striatum, how the actions are represented, how new states, how new actions might be learned. But based on neuroimaging studies and lesion studies, we know that this sort of model-free learning does happen in the human brain. There is furthermore some evidence that model-based reinforcement learning is also occurring in the human brain, and to get an idea of how that is located differently in the brain, I have highlighted here prefrontal cortex, which is associated with this sort of storing of the environmental dynamics and using this storage to simulate the world and based on these simulations take actions. The prefrontal cortex represents values and does value computation in this model-based reinforcement learning. However, again, we don't exactly know how these reinforcement learning systems are implemented in the brain. And I want to emphasize that it's not like these areas are alone responsible for these computations. They are just something that we know that are associated when these sorts of plannings and learnings are active in the human brain. Now, interestingly here, we see two very different types of reinforcement learning schemes. And now the problem for the human brain is not just to use these two reinforcement learning methods to solve the current task, but also to decide which one to use in which situation. So we could call this the meta-control problem. So we do not only have here two controllers that aim to figure out the optimal policy for different control tasks. We also have a meta-control problem that also needs to figure out which of these controllers to use in different situations. There are very interesting papers I have highlighted here too for your reference that deal with how this meta-control happens in the human brain. However, I won't go into that in any more detail. I'll just note that based on the evidence we have so far, we can fairly reliably say that reinforcement learning is something that happens in the human brain. There seems to be different types of reinforcement learning schemes occurring in the human brain. And at all times, constantly, we are getting more and more interesting research that sheds light into how reinforcement learning is implemented in the human brain. Now, cognitively, scientifically speaking, this is exciting because it lets us define human behavior in terms of optimal policies. And here is where we get into the human rational control. So we assume that humans are rational, but within certain bounds. By rational, we mean, in the case of humans, that humans attempt to discover and follow these optimal control policies. However, we shouldn't understand this optimality too broadly. Humans are biological machines, and we are really bounded by our environment in which we work. We are bounded by our bodies, and we are bounded by our minds. For example, our cognitive architecture has only a limited working memory capacity. This means that when we engage in model-based planning, it is fairly limited, or a working memory limitation bounds a lot how far into the future we can stimulate before we start forgetting the steps that we are currently imagining. This doesn't mean that we are suboptimal, it just means that we are bounded optimal. So the control policies that we need to figure out, they need to take into account these bounds of our own cognitive architecture and of the environment. Now, this is a hugely important idea because it lets us investigate human behavior. Also, when human behavior is biased, it lets us investigate human behavior in terms of optimal policies. So we get to ask if it looks like humans are not behaving optimally, for example, if they have bounds or if they have biases, we can ask, well, what might be the plausible bound candidates to explain these biases in human behavior or human thinking. Due to the vastness of this idea, I think there are a lot of different partially competing frameworks for investigating the human bounded rational nature. So there are topics such as computational rationality, emphasizing the computations that the human brain carries out. There's the cognitively bound rationality, which emphasizes the bounds imposed to human problem solving by its own cognitive architecture. Resource rationality, which emphasizes that biases in human decision making result from rational use of cognitive resources, etc. So there are a lot of different camps using this idea of bounded rationality and making the use of concepts of machine learning to describe human problem solving. Now, in today's topic, multitasking, the bounded rationality idea is applied to describe how humans decide to switch between tasks. So, for example, I might be writing a paper, itself a really complicated control task that requires planning, and it also requires the ability to control the keyboard of the computer and so on. And then suddenly I get an email notification. Now, reading an email and responding to an email is itself a complicated control task, but I also have here the meta control problem of deciding to either switch to the email or ignore it and carry on writing the paper. How do I solve this problem? How do I decide which task to take? Similarly, I might be driving and then suddenly I get a text message, and driving itself is a very complicated control problem. And reading a text message takes important resources that are required in driving away, but I still might take the chance and read the text message. Or maybe I need to check the navigator because a junction is coming and I need to decide whether to turn left or right. And there the meta control problem is deciding when to switch attention inside the car and when to switch attention back to the road. Now, these sorts of control and meta control problems, the difficulty in solving them both in the area of machine learning and in cognitive science is that the state spaces and the action spaces here get really, really large, which means that planning in them and learning them to begin with, it's very difficult. To help artificial and natural agents in these sorts of complicated and hierarchical decision making problems, we can employ the notion of hierarchical representation. Illustrated here in the top pane A is a so-called flat planning graph, where the agent needs to plan each step from the starting point to the goal point of getting an ice cream. Now, especially in humans where working memory capacity is very limited, you can imagine that when in real world tasks, these state spaces get really quick, really fast. We have a lot of different actions that we can take in each state. This planning through this flat graph is very, very difficult. To help a human being in that, we know that the human brain does something similar to these sorts of hierarchical descriptions and hierarchical planning. So we are able to compress the state space into more abstract state spaces, such that, as seen here in pane C, the number of steps that need to be taken from the starting point to the end point is manageable within our working memory limits. This is computationally more feasible, not only in terms of memory requirements, but also in terms of speed that it takes to plan through this hierarchical graph versus the flat graph. An important question for cognitive science and also for machine learning is the discovery of these hierarchies. Where do the hierarchical representations of the world come from? I won't go into it in more detail today. I'll just note that both in neuroscience and in cognitive science, there are very interesting recent studies that attempt to discover or figure out how the human brain discovers hierarchies and which parts of the brain uh, take part in this hierarchical representation and hierarchical planning. For my research interests, I'm not really currently that much interested in the discovery of the hierarchy, as I'm just utilizing the notion that we do have these sorts of hierarchical planning and representation schemes in our mind. So I use that notion of hierarchy and hierarchical learning and planning to solve or model how humans interact with complicated task environments that have technologies in them. So today's case is the driving and using an in-car device while driving. This device, it requires vision. It can be reading a text message, or perhaps it could be searching for some item on an in-car navigator display. So we specify the world, and the world may consist of the driving environment and the in-car device. There is some agent in working in interaction with that world, so it observes the world. Probably it only can make partial observations of the states of the world, so it has a belief that somehow reflects the state of the world, but may not be the same. The agent acts according to some policy with the world, trying to accomplish goals, such as driving safely. And now, because we are multitasking, that is, we have interleaved tasks, and we need to switch between these tasks, we can represent this sort of a situation by defining another agent that also observes the world and acts within the world. And the problem here in this presentation can be summarized as a conflict between these two agents. Perhaps they both, for example, require vision, such as when you're driving and when you need to do an in-car device search visually. Or maybe it's a motor control conflict where you need hands for both driving and responding to a text message. To solve this sort of meta-control problem of when to allocate different resources to different agents while multitasking, our idea is to employ this notion of hierarchicality and add a supervisor that develops its own control policy to supervise these agents and to decide who gets attention or other resources when. So what the supervisor does, it doesn't interact with the world per se. It observes what the agents are doing, and then it decides how the agents should act. It doesn't learn the agent's own control policies. It learns to manipulate, for example, slots in the agents such that it is able to manage how the agents employ their control policies. So we use this idea of hierarchical control policies to model multitasking in driving. And the idea here was that we employ the notion of optimality. So we assume that this sort of subtask and controller hierarchy discovers the optimal policy. First of all, it discovers the optimal policy for the subtask controllers, but it also discovers the optimal policy for the supervisory controller. And as a result, we would be able to describe how humans multitask while driving, if, again, we are able to define the bounds that bind the human driving. So what we did is to define the two tasks. We have a driving task, and then we have an in-car visual search task. In the driving task, the agent, driver agent, has some sort of a policy, pi. And here you note that I'm using the belief in the policy and not the state of the world. So we don't let the driver agent know the current driving state. It can only make observations. And based on its observations, it keeps a distribution, a belief distribution over all the possible states in which the driving task can be. In addition to observing the world, the driver agent has an internal simulation. So it has a model of the transition model of the real world. You might imagine a physics simulator. So if you are driving a car and you close your eyes, you are able to drive at least for a short while because you are using your internal physics simulator. And this belief update results in some sort of a distribution over all the possible states of the driving world. Similarly, we have a visual search agent that also holds a belief about the visual search task. Its task is to locate a hidden target by uncovering them by looking at these boxes. In the beginning, its belief is flat, so each of these hidden rectangles have equal probability of having the visual search target, and then the agent starts to uncover these by looking at them until it finds the correct element. So you will see that both of these agents require observation. Visual search agent is not able to proceed in its task if it doesn't have observation ability, that is, if it doesn't have the visual attention. However, the driving agent, thanks to its internal simulation, is able to drive while the visual attention is given to the visual search agent. But what happens here is because it's not able to make observations and because the world is noisy. The actions of the agent have noise associated with them. You can imagine driving a car. Your hands go like this all the time. And so the driving environment is noisy. There may be wind that changes the position of the car or the speed of the car. And very quickly, these sources of noise start to accumulate and deteriorate the belief that the agent has of the world. In order to emphasize this, we used what is called an augmented POMDB, in which we summarize the belief distribution into an augmented belief, which consists of two entities. One is the most plausible current state of the world based on the highest belief, and the other is the entropy of the whole belief distribution. And the driver agent learns its policy based on these two entities. And the idea here is that, or the insight is that the lower item in the augmented belief reflects the uncertainty that the driver has about driving. So we might say that without visual attention, when the driver agent is driving, this increases this entropy of the belief distribution. This means that there is accumulating uncertainty about the state of the driving world. What the agent has learned during training of policy, it has learned that when the uncertainty is high, that is when the belief distribution's entropy is high, the values of any actions are generally low. So there is a risk of accidents when the driver closes their eyes for too long. And we can employ this idea when we define the hierarchical structure. So the supervisor, what it does, it observes the current value of the optimal policy from the two agents, the driver and the visual search agent. So the supervisor can always keep track of how the driver is doing. When the values of the driver are going down, it knows that the driver agent is now very uncertain of the current road position, and the supervisor learns a policy that maps these values, subtask values, into actions that decide which of the agent gets vision. As we have defined the rewards such that the driver agent will get negative reward from driving outside the lane boundaries, and the visual search agent gets positive reward when it finds the target, and the supervisor gets the sum of these two subtask rewards. So the supervisor's reward is the joint reward of the subtasks. The supervisor learns a control policy or a meta control policy where it keeps the car in the road, but it still does visual search. Now to test this, we had participants driving in a simulator, and you can see there on the bottom of the primary screen, there is a small tablet that has the in-car search task. And I'll just show you one result here, and then I'm finished. What we observed, this is a very subtle effect, but it's statistically significant. For humans, when we increase the driving speed, the number of off-road glasses increases. And the model also predicted this. Now, this is understandable result when we know that the increase in speed decreases the off-road glass time. And this is, in a sense, quite understandable finding. So what this means is that because the car is driving faster, the uncertainty is accumulating faster, and that means that the agent, the supervisory agent, can let the visual search agent have vision for a small amount of time. But what we find here that is an encouraging result is that our reinforcement learning, hierarchical reinforcement learning agent was able to figure out this same control policy that the humans were able to figure out. And we didn't fit any parameters of the model into the human data, but regardless, we were able to find a lot of these effects where changes in the task environment result in adaptations in the human participants, and very similar adaptations are observed in the model. So to conclude, hierarchical reinforcement learning, it has neurocomputational plausibility and it has behavioral plausibility as a candidate for modeling human multitasking. It can be multitasking while driving, but it can also be, for example, switching between tasks when working on a computer. However, we must note that the exact computations that are carried out in the brain are not known. We don't know how the states are represented in the brain. We're not sure how the hierarchies are discovered to begin with, but it seems that we are on the correct path. Importantly, the supervisory control problem is only solvable via reinforcement learning for modeling human adaptation if we assume that humans adapt rationally to tasks and cognitive constraints. That is, if humans are bounded optimal. Thank you. Now, time for discussion.
So thanks, Jussi. There is already the first question is in the chat, which is from Anna. So do you want to say that brain does reinforcement learning? I could continue on this. I believe you actually said in the beginning that there is evidence for this. So yes. Maybe if I could continue on along this line, is that it makes a lot of sense to formulate the supervisory problem that you said for cases where there is limited resource, such as the attention. But so is there evidence, are there, I mean, we could think of the brain consisting of multiple different output modalities or multiple different bottlenecks, and then there could be control separately for each of these. One would be the attention, the other one would be memory, and so on. So is there evidence that are there multiple controls, or is there just one, and that would happen to be what we call attention?
Yeah, now, I'm not going to give any definite answer to that. I'm sure that the neuroscientists would have a lot more to offer to that question. I don't think that we should, or I don't think it's a very strong hypothesis to assume that each modality has their own controller or control policy. I'm more in the camp that these policies are discovered based on tasks, and the hierarchy isn't dictated by any existing circuitry. It can be discovered more freely. If it's a sharing of attention, visual attention, then that can be the hierarchy that is discovered. If it's sharing of some other modality, hearing, attending something with our ears, then that can be discovered separately. Of course, it needs some brain circuits to control what we are hearing, but I don't think that this is dictated model-wise prior to learning the hierarchy.
Yeah, thanks a lot. Antti also was answering the question. Do you, Antti, want to speak up, or Jussi cannot read it now?
Actually, now I can. Yes, to Anna's question, do I want to say the brain does reinforcement learning? Yes, I'm not often very confident in statements about the brain because you shouldn't be, but yes, the brain does reinforcement learning. We don't know exactly, or yeah, as I said, it's not simple. We shouldn't say that the brain does temporal difference reinforcement learning exactly how it is described in the Sutton and Bartle reinforcement learning book. That's too specific statement, but we do know that the brain does reinforcement learning.
Any other questions? While you are thinking, maybe I can use the opportunity and ask another one. So this is a more machine learning oriented now. So now I can see full well that this line of research is really important for cognitive science. So kind of modeling how people do decision making and so on, right? Then this is really a modeling problem. So your task for in that quest would be to design the models that enable you to explain why people do what they do, right? But then there is the kind of inverse question that could we build helpers to ourselves, so the artificial intelligence helpers that would be able to take into account how we are and help us given our limitations. And there is the big question that where do these models come from, right? Now, what you described now, you had to put some elements manually, kind of design the tasks that the user is probably solving. Do you have some thoughts on how to proceed along this route on constructing AI systems that would be able to take us better into account along the lines that you described?
So I think you had two statements there. The first one I agree completely. We should use this sort of idea to make better technology interaction. So for example, we might design an AI or an algorithm that figures out when to show the email notification to the user. So it has some sort of model of the user, and it knows that the user is currently writing, and it makes predictions about the values of the current writing task and the attention requirements, and it makes predictions of the value of the email and responding to it quickly. And so it is able to decide for the user when the attention might be shifted to the email from the other task. However, we can still write these by hand, so we are not limited by our inability to currently exactly know how these hierarchies are discovered. We can write the hierarchies by hand at the present to tailor them to specific tasks and still use that to develop intelligent helpers.
Yeah, thanks. Christian has a question there in the chat box. Do you want to say it aloud, or you see? I can also see it now.
Yeah, I can see it now. But maybe you could, in your own words, ask the question. Christian.
Sorry about that. The connection got interrupted. Well, first of all, hello. Thanks for your talk. Really nice. Well, for my perception here was, if I understood correctly what you've been doing, I wonder if it could be framed as a joint optimization of an intrinsic and extrinsic reward. So I can see that you have an extrinsic reward here to try to optimize individual per policy, the search task and the driving task. And you're switching between the tasks based on the quality of, or based on qualities of your latent state distributions, so the entropy in that case. Now, we have an intrinsic reward as the information gain. So the relative entropy between that latent state distribution before and after action, which could be related to this, in that you could perform a joint optimization of an intrinsic and an extrinsic reward, and use that to control switching between and I think, I mean, if you used information gain solely, that would be knowledge seeking, right, as an intrinsic motivation.
Yeah, actually I had at the time I had a model that also was rewarded from minimizing entropy, but in our case that's not actually relevant, because the uncertainty about driving is directly related to value. So that is, in a sense, completely redundant to reward the model from minimizing entropy. However, I'm sure that we could figure out a situation where we indeed want to optimize jointly for intrinsic and extrinsic reward. Yeah.
Thanks.
So Antti is answering me. Antti, do you have? Are you able to? Are you eating porridge still, or can you speak so much that you could actually say it aloud?
No, I'm here. I was putting it there so everybody sees. So I was just saying that something that when you say that putting in assumptions manually, well, I think that's to a certain degree needed in a practical case like this, especially when the agent, the helping agent, needs to take an active stance and make an intervention to the world. Then you would need in a data-driven approach, you would need a very exhaustive data set where basically you would intervene in all plausible human states in order to learn the consequences. And that's just super hard and even practically impossible. So I think we need to work with theoretical assumptions and put them into these models to solve these kind of practical problems like this.
Yeah, right. By the way, I didn't mean that it would be undesirable to put prior knowledge in the models. Of course, as we know, kind of all modeling needs both prior assumptions and data if the prior assumptions are not sufficient. What I'm just asking is, or after, is that if we want to build assistants that are able to help us beyond an individual task, kind of learning such an assistant in general will become impossible if we have to tailor each task separately. This was the conundrum of the old school AI, that you needed to actually build a model of the world in order to do anything. So there needs to be some kind of efficient or interesting midways or compromises where things work well. We can specify only little and learn the rest from data and so on. And of course, I suppose nobody knows. I mean, this is the research direction. Just wanted to hear your ideas, and both of you expressed very nicely. Thanks.
I think to add on that, I think applied research, such as what we're doing with Jussi, often tends to look at some particular very well-controlled conditions where you have, for example, the driving speed, and then you have a very finite set of conditions, and you try to fit the model there. But what's interesting is that how much further can you go from there? If you think about this as a cross-validation setting, then what kind of leaps could you take in a valid way? We should be testing our models from that perspective. That if the agent wants to make an intervention that was not part of the model fitting, how good could it do, right, in that scenario?
Good. I think it seems we are stealing Jussi's show now by talking me and Antti. That wasn't
No,
intentional.
I don't think this is my show. I think this is machine learning coffee seminar. And it sounds like it is.
Yeah, good point. I think we are running out of the time, so let's thank Jussi very warmly. Very, very nice talk.
Thank
Thanks
you.
for
Thank
coming.
you.